welcome back. We're at part 3 now of our lecture about wakes. And so far your book has mostly been talking about the N.O. model, but there's a second model that we should be comparing it to, and that's the so-called Ansley model. And this becomes a mess, because Ansley model is a much more complicated story in terms of the mathematics behind it. It becomes more of a computational fluid dynamics type model, where you can't just look at the equations and make sense of even like how linear the terms are and things like that. This becomes something where the math has to be done computationally rather than, like on a computer numerically, rather than something that can be solved like on paper. And that's okay. Lots of things in atmospheric science work out to be, and lots of things in fluid mechanics work out to be more complicated that can be solved on a piece of paper. It would be okay if some solutions to this existed. If we could actually say, hey, yes, in general we can't solve this except, numerically in a computer, but actually at the special case of at this location or under these wind speed conditions or whatever, we'd at least have a solution there. And it turns out that there are a few such things, and even the few such things that there do exist for the Ansley model are fairly terrible. Your book actually shows a handful of examples in the text of situations where, okay, under these conditions we can actually say Ansley model tells us something without actually, running a computational model. Now, for example, if we go on to page 141 in your textbook, equation 7.11 shows us an expression that there is an analytic solution for. This is supposed to be the wind speed at a distance 2 rotor diameters downwind from the turbine in the Ansley model. And it has to be at like the same height and the height of the hub of the turbine, as well as like straight downwind, not off to the left or to the right. It exists. It's fairly horrible, but it can be done, and it can be computed, and we could do it. And we could take like the same stuff that we did for the N.O. model for exercise 7.1, I think it was, and we could actually plug those same numbers into this one specific case of the Ansley model that can be solved analytically, and run the numbers, and you get that there's a wind speed at 200 meters downwind for that same set of conditions. Let's actually compare the two sets of results. Now that graph, that Excel chart that I have there with the blue curve on it, that was the wind speeds being predicted by the N.O. model at 200, 300, 400, or whatever, however many meters downwind. And Ansley's prediction, I just sort of drew on there a circle to show you what it's predicting in that one situation of that analytic possibility. We'd have to run the model, the Ansley model, in a computational way to get the other speeds, at different distances, but right there we can do it just with calculators. And what I'm noticing is that they are nowhere near alike. The estimate from the Ansley model is ridiculously low compared to the estimate that comes from the N.O. model. The spot on that, the red circle, is way lower on the y-axis than it is on the blue curve there. So at 200 meters downwind from the turbine, Ansley is predicting something like 4.6 meters per second wind speed, and N.O. is predicting something like 7 meters per second wind speed under exactly the same conditions, and that makes me stressed. Because these are both respected, successful, widely used models. Why are they giving us such radically different answers? And the answer is because they're kind of telling us something very different. See, remember, N.O. is computing a single wind speed associated with any given distance downstream. So, for example, that black circle that I have on there, that is the wind speed that under this set of combination of conditions with UI and Z0 and all that stuff, we plugged it in for our rotor, our thrust coefficient and all that stuff, and we got that wind speed at 200 meters. That is a single wind speed at that distance. So what we're doing here, let's actually kind of make this work. What I've done is I've taken that same drawing that we've had before of a view of a top view of a wind turbine's wake, and what I've done is I've kind of stretched and swooshed the diagram so that it kind of matches to scale better. So like the turbine itself now is at about, you can kind of compare the two graphs that I've got there. So like see how the turbine itself, you can like slide down and see that that's at 0 meters, and then the whole thing extends farther and farther down, and so on. Okay, if we actually zoom in and look at what we're seeing at, let's say, 200 meters up into the wake, what N.O. is telling us is it's giving us a single wind speed at that distance from the turbine. That's UW of x, UWX. At that x, everywhere along that little black line that I just drew in there across the wake, NO Jensen is saying we have the same speed. So everywhere along that little line, which is 200 meters downwind from the turbine, we're having a wind speed of exactly whatever that works out to, 7.1 meters per second or something like that. And then outside of the wake, like in the two little places there that I just drew little red lines in, also 200 meters downwind from the turbine, but not inside of the wake, NO Jensen gives us a speed there too. It happens to still just be exactly UI. It's unchanged by definition. Okay, so if we were actually going to take the wind speed at different, if we took an anemometer or something like that across the wake, from left to right across the wake, I mean like a cross-section of the wind speeds that we'd encounter, it'd look a little bit like this graph we have in the bottom here, where like, you know, we go across the wind, across the wake, we'd at first have a high wind speed of about 10 meters per second, and then once we got into the wake, it would dip down to whatever the wind speed of UW of x, which is that black part that I drew in there. It happens to be about 7 meters per second at this location. And we'd cross the middle of the wake, and then we'd go on to the right side of the wake, and then when we touch the edge of the wake, the wind speed would jump back up to 10 meters per second. See how the function is just a little boxcar like that? It's just showing that there's like a wind speed that's outside the wake, and then there's a single wind speed inside the wake, and then there's another wind speed outside the wake on the right. It's simple. It's easy to picture. Is it terribly realistic? No, not really. That's why we have the Ansley model. The Ansley model is a whole lot more complicated. Remember, lots of fluid mechanics, lots of computational physics and so on going on to it. And what Ansley is predicting with that red spot right there, that's just the wind speed at the very center of the wake, farthest from the edges of the wake, and that's going to be a different story. So again, I'm going to put that same picture stretched in there of our wake, so that's kind of there to scale, and let's zoom in so we can see where that location is. Well, that estimate that we got from the Ansley model was just the wind speed at the very center of the wake from left to right. And from top to bottom, too. It's basically directly behind the hub of the turbine. Well, that's going to be the slowest wind speed along that cross-section, because that's the place farthest from the edges of the wake where higher momentum air is being transported in by turbulence. That's going to be the place where the wind speed is slowest. To the left, to the right, above or below that location, right behind the hub, the wind speed is going to be greater. In fact, it's going to have kind of a Gaussian distribution. So again, this is another figure that I took from your book there, and I have highlighted what the Ansley model says about the speed of the wind as you go from the left side of the wake, into the wake, to the middle of the wake, and then to the right side of the wake, and then out of the wake. Alright, so as you go across the wind there, you see you have this sort of Gaussian distribution to how the wind speeds are going to be. They're going to be a wind speed of UI, 10 meters per second, when you're way far to the left of the wake. And then as you get closer to the wake, you start experiencing the edges of the wake. You start getting wind speed slowed down a little bit, and they continue to slow down until you get to the center, where the wind speed is at its slowest. It's about 4.6 meters per second in this example. And then as you cross to the right side of the wake, and start getting farther from the central axis of the wake, the wind speeds are increasing until you finally get back out to UI, the initial wind speed, back off to the right of the wake. Oh, okay. Well, that actually looks a whole lot more realistic, but it's a whole lot more computation involved in getting that to work too. So, we have these two different models who gave us two different ideas about what the profile of the winds will look like as you go from left to right across the wake. Ansley and NO Jensen. Now, if you actually integrated the wind speed across that track, what you'd find out is both Ansley and NO Jensen have the same total or average or whatever you want to say reduction in the speed of the wind. They have to. That's what has happened. We have reduced the wake represents a reduction in the speed, the amount of momentum being carried by the air caused by the thrust coefficient of the turbine. So they're both giving the same total amount of reduction of the wind speed along that transect across the wake. They just distributed it slightly differently, with Ansley distributing it almost certainly more realistically than NO Jensen is. On the other hand, there are benefits to what Anno Jensen did. I mean, Anno Jensen has a very well-defined edge of the wake on the left side and on the right side, and top and bottom for that matter, too. Whereas, for the Ansley model, you'd have to come up with some way of deciding what you're going to define as the edge of the wake. Well, I mean, that's probably true in the real world, too, right? In the real world, you'd probably have to figure out what you're going to do. If you had observations from some kind of piece of equipment, you'd have to decide whether you wanted to say that that was inside or outside the wake. They're two very different ways of solving the problem that come up with similar but not exactly the same answers with pros and cons to both. I mean, the Anno Jensen model, a whole lot simpler, and gives, frankly, pretty good answers that are pretty consistent with the much more realistic but much more complicated Ansley model. And one would wonder then, what are we going to do with this? Is it going to matter which one we use? Well, kind of yes and kind of no. I mean, if we really need to know, like, some distance behind the turbine, and also 10 meters to the left, I suppose Ansley model is going to be your right choice there. But if you're just talking about, hey, there's a second turbine downstream from this turbine, how much is that going to be affected by its power, by the upstream turbine? Well, the second turbine downwind is catching wind from a fairly wide range of angles, right? I mean, from a wide range. It's catching parts of the wake of the one above it, the one upstream of it. So, well, I mean, in some places, Anno Jensen is overestimating your real winds, and in some places it's underestimating, but it averages out to being right anyway. So it probably, for the point of view of like a wind power estimation as to how much this turbine is affecting this downwind turbine, probably doesn't really matter all that much, which model you use. Before we go on to our fourth part of this lecture, let's do a couple quick questions. Question 9. In the Anno Jensen model, the wind speed at the center of the wake is probably A, overestimated, or B, underestimated. Oh, what I want you to do is to remember that we think Ansley is probably closer to right, so then what does that tell us about the error in Anno Jensen? Is Anno Jensen overestimated or underestimated? Make a choice for those two options and get a little feedback before you move on to question 10.